So we're going to be looking at bonding basics in this video and understanding the overall general ideas of the types of bonding that will be encountered in chemistry. So before we get into the different types of bonding, let's go ahead and look at a couple of tools or symbols that we utilize and need to understand in order to discuss bonding more thoroughly. So the Lewis dot symbol is basically an electron configuration notation that only represents the valence electrons. And what we do is we take the element and we apply the valence electrons to one of four sides. Okay, so if we write the element symbol, side number 1, 2, 3, and 4 are all equivalent. So in this case, if we want to write the Lewis dot symbol for lithium, we're going to take lithium and place the single valence electron that it has on one of the sides. All of the sides are equivalent, so any side will do. However, a lot of times we start with the right-hand side first. Now, something that also needs to be thought about or taken into account is that when we are writing the Lewis dot symbols, we also do not pair up electrons if there is an available side. So if we look here at sodium, when we go from sodium to magnesium, magnesium has 2 valence electrons. So instead of pairing up the 2 electrons on one side, we put them as far away from each other as possible. Okay. Aluminum has 3 valence electrons, so notice we've distributed the 3 electrons to 3 independent sides. Silicon has 4 valence electrons, so there's 4 independent sides in which those electrons have been applied. And it's not until we get to phosphorus that we notice that we start the pairing up process. So just like we would apply the rules in terms of not filling orbitals with pairs of electrons if there's empty orbital seats, we're going to kind of apply that thought process here when we write our Lewis dot symbols. Now, one of the main features, the main driving forces of bonding and the reason why all these interactions occur is because atoms want to have an octet. And basically, that brings us to the octet rule. The octet rule states that elements tend to gain or lose electrons until they have 8 valence electrons. And there are exceptions, and we'll talk about them here in a second. But basically, the reason why all of the elements on the table want to have their octet is so that they can have the stability that the noble gases experience by having those completely filled outer shells. Okay, so in order to do this, there's going to be sharing that occurs, or sometimes atoms will gain or lose electrons. And so in situations like that, obviously we're going to be creating ions. If we've lost electrons, they'll be positively charged. If we gain electrons, they'll be negatively charged. And that will bring us into the specifics of the type of bonding we will be discussing a little bit later into the lecture. So if we go ahead and we look at some of our exceptions to the octet rule that was mentioned earlier, beryllium, boron, helium, and hydrogens are all very common exceptions. Okay, beryllium is happy with only having 4 valence electrons around it. Okay, boron can be content with 6. Okay, helium, as we know, those 2 valence electrons that it has is unique. Okay, and hydrogen can also be happy with 2. So these are our exceptions to the octet rule that are kind of specific and kind of randomly distributed throughout the first and second rows. However, there are also exceptions to the octet rule in row 3 and below. And we talked about that when we discussed Lewis structures. Basically, row 3 and below can have an expanded octet, so they can take on more than 8 electrons and subsequently give you a unique set of bonding because of the new orbitals that are accessible. So what is chemical bonding? So chemical bonding on its basal level is an attraction between the outermost electrons in an atom and the nucleus of a different atom. Okay, so if we were to look at a little diagram, okay, if I have this atom here and this atom here, what's actually happening is that the valence electrons that are in this atom right here are being attracted to the nucleus in the atom over here. And the same concept is occurring for the electrons that are in this atom and the nucleus that's on this side. So basically this mutual attraction is what's guiding or what's driving bonding. Now, there are three types of bonding that we will be looking at. We'll be looking at ionic, covalent, and metallic bonding. Okay, and all of this bonding, all three of these types of bonding, result from the interactions of an atom's valence electrons. So those outermost electrons are what are going to dictate the type of bonding that occurs. Now, the other reason why the bonding occurs is because every atom on the periodic table wants to have the stability that's conferred from having a completely full outer shell. So everybody, or all of the atoms on the periodic table, want to be like the nearest noble gas because of the stability that is provided. So let's go ahead and let's look at ionic and covalent bonding in a very generic side-by-side type of way. Okay, so in ionic bonding, electrons are transferred, while in covalent bonding, they're shared. Okay, so these are probably the most important things to understand in terms of your comparison between ionic and covalent bonding. Okay, ionic bonds are normally found between metals and nonmetals, or more specifically, a cation and an anion. So obviously we can have examples where we don't have a metal, but generally speaking, a metal and a nonmetal is what's going to be present in an ionic bond. Okay, covalent bonding is represented usually by having two or more nonmetals bonded to one another. However, metalloids can also be involved in covalent bonding. Okay, so ionic solids or ionic compounds are typically solids, while our covalent compounds can usually be either solid, liquid, or gas. Ionic solids have a very high melting point. We'll talk about why a little later. Covalent compounds usually have very low melting points, and we'll discuss that in detail. But there's other features. There's solubility. There's electrical conductivity. These are all things that are usually going to be specific to different types of bonds. And so, when we look at the solubility of water, a lot of times we could take an ionic solid, such as sodium chloride, put it into water, and it will dissolve into its component ions. Covalent compounds, that's not usually the case. And so these are all features, or just kind of a generic look at both ionic and covalent bonding. We're going to take the same look at metallic bonding. And in metallic bonding, there isn't a sharing of electrons, there isn't a transfer of electrons, but there's an actual electron sea. And we'll look at a diagram that helps us understand that in a little bit here. Okay, metallic bonding occurs between, surprise, surprise, metals. The physical state, metals are usually solid. Obviously, there are some exceptions, or there is an exception. Mercury is a great example there. But the melting point of most solids is fairly high. They're not usually soluble in water. They'll usually conduct electricity, and they're able to be shaped and formed and are usually pretty shiny. So metallic bonds are basically just one of those three types of bonds that we're going to be looking at in detail. So if we take a closer look at metallic bonds, basically you're going to have attractive forces that are going to be occurring between delocalized electrons. So what delocalized means is that they're not, shared just in between two atoms. They're randomly distributed. Okay, and basically these electrons are randomly distributed through cations of the metals. Okay, so basically the reason why we call it the sea of electrons is because if we look at our cations as maybe little lifeboats, the electrons that are randomly floating around, these delocalized electrons, are actually kind of like a sea that those lifeboats are floating in. So the fact that these electrons are delocalized gives metals some of their features, such as malleability and things of that sort. When you take a hammer to a piece of metal, the metal doesn't crumble into a million pieces, it usually just forms a dent. And the reason why it just forms a dent is because as soon as we hit this atom with an object, the atom may move, okay, but instead of breaking a bond or causing issues, what happens is that all of the electrons that are delocalized just redistribute. Okay, so you've altered the shape of the piece of metal, but the electrons and things of that sort just kind of reorient themselves and adjust. Also, this affects the conductivity, the flow of electrons that are able to go through the metal. That's why the metals are conductive. So basically, this metallic bonding in this sea of electrons is basically what gives metals their properties.